Welcome to this video in which we are going to expand our understanding of linear independence and to look at other ways that linear independence can be, or dependence can be determined, right? So previously the definition of linear independence requires us to solve an actual homogeneous system and see if we have only the trivial solution or if we have at least one free variable. And while that process will always work, again, there are other things that we know that can actually make our job a lot easier as it relates to linear independence or linear dependence. All right. So we're going to go through a couple ideas and just try to connect this new concept to many of the older concepts that we've looked at, some of them going back, at the very start of our journey. So let's say we have only two vectors. So what if we have, given v1 and v2. So if I were just to give you two vectors, what could we look for, right? Is there some kind of clue, something easy that we could check to see if they are linearly independent or linearly dependent, right? Well, suppose they are linearly dependent, right? So suppose v1 and v2 are, let's go back here, let's say are linearly dependent. Well, what does that mean? Well, it means I can find a non-trivial solution to this equation. So it means that this equation has non-trivial solutions. Okay, that's great. But what does that mean? Well, if it has non-trivial solutions, it means I can find a value or values of C1 and C2 that are not both equal to 0, right? So that this implies that C1 and C2, right? Assuming the vectors are not the 0 vectors, and I'll say that in a second. So C1 and C2 are not both 0, right? So this is assuming that v1 and v2 are not equal to the 0 vector, right? So it means these constants are not equal to 0, but again, we're able to form this linear combination and create the 0 vector. Well, if that's the case, if neither of these coefficients are equal to 0, then it means I could actually solve for one of these vectors. So let's say I wanted to solve this equation for v1, right? So solving for v1, what I would do is I would subtract c2 v2 from both sides. So I'll have that c1 times v1 is equal to negative c2 v2, and because this constant is not 0, I can divide both sides by it. So therefore, v1 is equal to negative c2 divided by c1 times v2. So these two constants, again, our constants are not both 0, and I'm dividing one constant by another constant, which leads to a third constant. So I'm just going to relabel this and call this whole thing C3. It's just another constant. So therefore, V1 is equal to C3 times V2. Well, what does this mean? Well, it means if the vectors are linearly independent, then it means one of them would have to be a scalar multiple of the other, right? Now that's easy to check. right? We don't need a linear system, a formal linear system to determine if two vectors are scalar multiples of each other. So here are the two consequences of this observation, right? So this means, and now we can actually say it this way: if V1 and V2 are scalar multiples of each other, so are scalar multiples of each other, that means one vector is a non-zero scalar multiple of the other one, right? Then V1 and V2 have to be linearly dependent. So then V1 and V2 are linearly dependent. So this is one of those things where if you're only given two vectors, it's relatively easy to check. And what if they are not scalar multiples of each other? Well, that's the beauty of this. It's either they are or they're not. So if they're not scalar multiples of each other, then the vectors would have to be linearly independent, right? So if V1 and V2 are not scalar multiples of each other, then V1 and V2 are linearly independent. Right? Such an easy consequence. So with two vectors, it's a lot easier if we just check to see if they're scalar multiples of each other or not. So let's do a quick example of this fact. In fact, what we can do several examples, right? And what I'll do is I'll just give you pairs of vectors, some that are scalar multiples of each other, which would make them linearly dependent, and some that aren't scalar multiples of each other, which will make them linearly dependent, or independent, sorry. So our first one, for our first pair, so let's say V1 is equal to 2, 3, and then V2 is 4, 6, right? And notice all I did was I basically took this vector and I doubled it to make this second vector. So the fact that they are scalar multiples of each other, what that means is they are linearly dependent, right? So since, let me write it this way, V2 is 2 times V1. Notice what I can do now. If I subtract V1 from both sides, so this implies that negative 2 V1 plus V2, that would have to be the zero vector. So there is our non-trivial solution, right, to this equation. So if I multiply the first vector by negative 2, and if I add the second vector, then I'm guaranteed to get the zero vector, right? So these two vectors, right? So since that V1 and V2 are linearly dependent, right? So yeah, once you recognize that they are scalar multiples of each other, then there is a non-trivial way of combining them in order to get the zero vector, right? What about, let's say, this pair? So V1, let's say we have 1, 1, 1, negative 1. And then V2 is 0, 1, 2, 0, right? Well, it's pretty clear that these two vectors are not constant multiples of each other, right? Because if you think about it, the only constant I could multiply the first component by to get 0 is 0. But if I multiply the whole vector by 0, I am not going to get this vector, right? So there's no scalar multiple that I can use to multiply v1 in order to get v2. So because of that, if I wanted to combine these two to get the 0 vector, the only coefficients I could use are 0 and 0, right? So since v2 is not some constant times v1, right? Then these vectors are linearly independent. Right? So these vectors are linearly independent, right? So vectors are either scalar multiples, which will make them linearly dependent, or not scalar multiples, which would make them linearly independent, right? So for two vectors, fairly straightforward, easy to check. The difficulty comes when you're given more than two vectors, right? So let's do that and say, let's suppose now we are given v1, v2, v3, vm, right? How can we check to see if these vectors are linearly independent or dependent? Well, once you have, multiple vectors more than 2, so let's say my m is greater than 2, we can actually rely on a couple things that we know about linear systems and matrices and so forth. So for instance, let's form the matrix using these as the columns of the matrix. So form matrix A by using the VI's as columns, right? In other words, A is going to be this matrix. So set up your matrix, put V1 there, put V2 there, put V3 there, put Vm there, right? So that's our matrix. So basically what we can do, we can represent this question about the solution to our homogeneous system in matrix form. So it boils down to this. What is the solution set of or A now, and then I'll just use the typical X to represent our variables, but now it's a homogeneous system, right? So the question is, does this system have only the trivial solution, or can we find a free variable and hence infinitely many solutions? Well, if you think about it, if our matrix is a square matrix, right? If we have the same number of rows and columns in our matrix, then we can use some facts about invertibility or the determinant to actually answer this question, right? If A is invertible, in fact, let's back up a little bit and say if the determinant of A is 0, then we know that A inverse exists, right? And we could figure out the solution by simply multiplying both sides by the inverse, right? So we have this. Our x will be A inverse times the 0 column. But when I multiply my inverse and the 0 column, I am going to get just 0. So this would tell me that my solution would have to be just the trivial solution. So what this means is if the, let's back up and say, I'm sorry, if the determinant is not 0, right? If the determinant is not 0 and the matrix has an inverse, then the solution has to be the trivial solution. And that makes my vectors linearly independent, right? All right, so let's write that down. So since we have only the trivial solution, this implies that V1, V2, Vm are linearly independent. Right? So we can use these two concepts, invertibility or having a non-zero determinant. If the coefficient matrix ends up being a square, we can utilize this fact and show that the columns have to be linearly independent, right? Now, what if the determinant is not 0, right? Well, if the determinant if the determinant is 0, then the matrix doesn't have an inverse, which means A is not reducible to the identity. So you would not get your n pivots, and you would have to have a free variable. Now what that means is if the determinant of your matrix is equal to 0, then the vectors would have to be linearly dependent. Right? So let's write that down. So if the determinant of my matrix is equal to 0, right? Then this means that your vectors v1, v2, vm are linearly dependent. Right? Very easy check. Now, but again, remember, the determinant is something that is unique to square matrices, right? But what if the coefficient matrix isn't square? I mean, we've seen systems where we have either more rows than columns or more columns than rows. Then what could we check in that case, right? Since the determinant wouldn't be defined for a non-square matrix, what other concept have we looked at that could possibly help us? Well, this is where the rank and the nullity come in. Because remember, the nullity represents the number of columns that don't have a pivot. So if that column doesn't have a pivot, then it means you have at least one free variable, right? So we can say this. So if the nullity of the matrix is equal to 0, right? So if your nullity is equal to 0, that means you have no free variables. So again, you will only have the trivial solution, right? So if the nullity of the matrix is equal to 0, this implies that there are no free variables, and if there are no free variables, then in a homogeneous system, the only solution you have is the trivial solution. So which implies further, only the trivial solution Therefore, the vectors are linearly independent. So v1, v2, dot, 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 vm are linearly independent. Right? Now remember, to find things like the rank and the nullity, we have to essentially determine how many pivots we have in an echelon form, right? So we will have to do some reduction there, but we don't necessarily have to go to RREF. We just have to go to REF and see how many pivots we have. And then to kind of wrap this up and say, well, what would happen to the nullity if the vectors were linearly dependent? Well, what that means is you'd have at least one free variable. So that means your nullity would be greater than or equal to 1. So if the nullity of your matrix is greater than or equal to 1, then this means there is at least one free variable. So there is at least one free variable, which means you have to have infinitely many solutions, right? That's what free variables are. You have lots and lots of solutions, so there would be non-trivial ways to combine the vectors to get the zero vectors, right? So you'll have infinitely many solutions. That means you can find different values for C1, C2, C dot dot dot, Cm, and then therefore the vectors, so V1, V2, dot dot dot, Vm would be linearly dependent, right? I think this is such an important concept and what we're looking at, because pretty much every concept that's related to like linear systems, matrices, so determinants are all wrapped up in this idea, right? Whether we can use the determinant, that depends on whether we have a square matrix or not. If we don't, then we have something a little bit more general, this idea of the nullity, because that's exactly what the nullity counts. It's the number of free variables. So if you have no free variables in a homogeneous system, then you'll only have the trivial solution. If you have at least one, then you won't have just the trivial solution. And then we can tie it back to the concept of linear independence or linear dependence. All right? Let's end by looking at a couple examples where we get to utilize these different concepts. Right? So let's see example or examples, since we can do a few. Right? Let's see. Are the vectors, and let's just write our vectors here, 1, 1, 1, 1, 2, 3, and 1, 1, 2, are these vectors linearly independent or linearly dependent? Question mark. Again, explain or justify. Right. Okay, so here are our vectors. So what are we going to do? Let's form, so there are more than two vectors, so we can't just check for scalar multiples. So let's form our matrix. So let A be equal to the 1, 1, 1, 1, 2, 3, 1, 1, 2. So this is the idea of forming our matrix using the columns that are the vectors that are given, right? And since we have a square matrix, let's go ahead and check the determinant, right? I mean, that's relatively easy to find. We have lots of ways of computing the determinant. So the determinant of A is this, right? So we got our 1, 2, 1, 1, 3, 2. Now, with something like this, we could easily use our cofactor expansion using the first row. It's not too difficult. But just to, again, do another example of using the elementary row operations, let's try to make this triangular. Let's see if we can make this triangular and see what happens. So I have my pivots there. Let's do negative row 1 plus row 2, negative row 1 plus row 3. Right? And we know that doing these two operations does not affect the value of the determinant. So we'll have our 1, 1, 1, 0, 1, 0, and then 0, 2, 1. All right? So not quite triangular yet. But let's now eliminate the 2. So do another times row add. So if we do negative 2 times row 2 added to row 3, that will eliminate this entry. So we'll still have 1, 1, 1, and then 0, 1, 0. And then now when I multiply the second row by negative 2, add it to the third row, I'll have 0, 0, 1. Here we go. I have an unbalanced thing here. I have one vertical bar, one square bracket, so let's fix that. So now that we have a triangular determinant, we can find that determinant by multiplying the elements on the main diagonal. So 1 times 1 times 1, that's equal to 1. So since the determinant of our matrix is not equal to 0, then if we were to solve the corresponding homogeneous system, we would get only the trivial solution. That means these three vectors are linearly independent, right? So there is no way to combine these three vectors, right? In no non-trivial way to combine these three vectors in order to produce the 0 vector, right? So these vectors are linearly independent. All right? And that's because our matrix, what this means is our matrix has an inverse, and once your matrix is invertible, then any linear system with that coefficient matrix has to have a unique solution. All right? All right, let's try something like, let's look at these. Second example. Are the vectors, let's see here. Let's do some vectors in R4. So negative 1, 2, 1, 1. So are these vectors that one, and then 1, 4, 0, 1. And then let's say 2, 2, negative 1, 0. So are these vectors linearly independent or linearly dependent? It's one or the other, can't be both, right? And then, of course, explain. All right, well, let's go ahead and set this matrix up, right? So let's say we're going to try to do a matrix approach on this. So negative 1, 2, 1, 1, 1, 4, 0, 1, 2, 2, negative 1, 0, right? Now, the problem with this is not a square matrix, so we can't use the determinant approach. So what we would have to do is try to reduce this and see how many pivots are we going to end up with. Are we going to end up with a pivot in every column? if that's the case, then the nullity would be 0, and then these vectors would be linearly independent. But if we end up with a nullity that's 1 or bigger, then the vectors will be linearly dependent. All right? So let's see, well, we can multiply the first row by -1. So let's go ahead and do that. So let's do -1 times row 1. That gives us 1, -1, -2, and then the other 3 rows stay the same. And then I can use this as my pivot, and for sure I can eliminate the 2, the 1, and the 1. So if I do -2 times row 1 added to row 2, and then negative row 1 added to row 3, and then negative row 1 added to row 4, right? I know the first row will stay the same. Second row becomes 0, and then 6, and then 4. Oh, wait. Let's see. I'm looking at. I don't know. This is that. Oh, that is right because I have -2 times -2. That's 4, and then plus 2, so that's 6. That's also a 6. And then negative row 1 plus row 3. So then this will give me 0, and then 1, and then 1 as well. There we go. And then the negative of this added to this. So we have 0, and then we have 2 and 2. All right. Now, let's try to get a pivot right here. So we can multiply the second row by 1/6. So 1/6 times row 2. That's 1, -1, -2, and then 0, 1, 1. And then below I have 0, 1, 1. And then below I have 0, 2, 2. So what's going to happen is when I eliminate this 1, I'm going to automatically eliminate this 1. And when I eliminate this 2, I'm going to automatically eliminate that 2. So let me write down the formal operations here. If I now take negative row 2 and add it to row 3, and if I take -2 row 2 added to row 4, this is what I end up with. 1, -1, -2, 0, 1, 1, and then 0, 0, 0, and then 0, 0, 0, right? So now we are in an echelon form, right? It's not reduced, but it is row echelon form. And in this REF, I have only 2 pivots, right? So let's write down what we know as far as rank and nullity. This tells me that the rank of my original matrix is 2, which means the nullity, and remember the relationship between the rank and the nullity, it always adds up to the number of columns. So I have 3 columns here, but only 2 of them have pivots, so I have 1 column which would be considered free. And because of that degree of freedom, the homogeneous system would have to have infinitely many solutions, right? So because of this, because the nullity of our matrix is greater than or equal to 1, so this implies that my original vectors, so these vectors are linearly dependent, right? I think this is such an important concept, and I think, even if, and it will take some time for you to really think it through, but you do see now how to answer this one question. We can rely on almost every concept or topic that we've covered up to this point, right? And such is the nature of linear algebra. It's seemingly different concepts, but they're all tied together by a few key results. And if you understand those few key topics, everything follows from then, right? So think it through and do some examples, ask questions, and also come back for the next video. See you then.